Hi, let me ask you, have you been facing a hard time factoring numbers? When you factor out small numbers, medyo kaya pa ng trial method. Pero when they give you a number like 98,271, mapapakamot ka lang sa ulo, di ba? So, here comes our topic for today. Pollard Rho Factorization Method. Pollard Rho Factorization Method was introduced by John M. Pollard in 1974, originally as Monte Carlo algorithm. It is particularly effective at finding small to medium, non-trivial or a prime factor of a composite number. When you say a composite number, it has other factors other than 1 and itself. Moreover, it works by simply generating a pseudo-random sequence modulo and computing its GCDs. Apart from it, Rho means the letter P in Greek letters. Hence, the Pollard Rho factorization method generates a sequence of modulo that forms a tail in the loop due to the repetition that looks like a row or a P, just like in the diagram, diba? Magsisimula sa maliit tapos sumalaki dahil hindi pwede lumagpas sa N, iikot lang siya, then it forms the row. Ang promising, no? Lorraine, paano ba yan gumagana? Turuan mo naman kami niyan.
Ayan! For better understanding, proceed tayo sa definitions and key concepts. Again, a Pollard Rho is a factoring algorithm used to find a non-trivial factor of a composite integer n, especially effective for numbers with relatively small prime factors. This method requires some various key concepts. First is the polynomial function f of x. In this case, we usually use the polynomial function x squared plus a, where a is not equals to 0 or negative 2. Pero bakit nga ba yun yung palaging ginagamit na function? We use this function because it is easy to compute, where you just square and add constants. That makes the sequence the random modulo n. X squared plus a usually creates a long tail plus loop, giving the Rho-shaped structure we exploit with GCD. Next is the starting point and the generated sequence. Our starting point, denoted as x sub 0, are often chosen randomly or as a small integer like 2. Our goal is to find a non-trivial factor d of n where d is less than n. To find d, we needed this recursive formula. X sub k plus 1 is congruent to f of x sub k modulo n. Later, the next reporter will show you an example to help you understand how to use the recursive formula with initial value. Here in Pollard Rho factoring method, if x sub I is congruent to x sub j modulo d, where I is less than j, but x sub I is not congruent to x sub j modulo n, then v divides x sub j minus x sub I, and the GCD x sub j minus x sub I and n produces a non-trivial factor of n. To better understand this statement, I prepared an example. Let n is equals to 91 with the factor 7 times 13. Suppose the algorithm produce x sub I is equals to 54 and x sub j is equals to 12. These numbers were obtained through the recursive formula. Now we compute the GCD. The statement above says that the GCD x sub j minus x sub I and n produces a non-trivial factor n. The GCD negative 42 and 91 is equals to 7. Therefore, 7 is the non-trivial factor of n. We now check the congruence modulo to check if it satisfies the congruence. 54 is congruent to 5 modulo 7 and 12 is congruent to 5 modulo 7. As you can see, the modulo 7 provides an equal congruence. So x sub I is congruent to x sub j modulo 7, and 7 divides 12 minus 54. But clearly 54 is not congruent to 12 modulo 91 since 12 minus 54 is equals to negative 42 and 91 does not divide 42. For the next slide, we also have refined version of the previous algorithm. The previous algorithm has the disadvantage that we need to compute x sub j minus x sub I and n for every distinct pair x sub j and x sub I until a non-trivial GCD occurs. Instead of checking all pairs, x sub a and x sub j, we only check GCD of x sub 2k minus x sub k and n where k is greater than equal 1. Why this work? If x sub I is congruent to x sub j modulo d, where I is less than j, then the sequence repeats every j minus I steps modulo d. So for some k, x sub 2k will catch up to x sub k in the cycle modulo d. Then x sub 2k is congruent to x sub k modulo d. So the GCD x sub 2k minus x sub k and n will reveal d. To help you better understand this, the next reporter will show more example. Miss Michiko, you may now proceed.
And for better understanding, I will elaborate what was discussed by showing step-by-step examples of Pollard Rho factorization. Let's start with example number 1. We have f of x is equals to x squared plus 1 modulo 91. Let's start with step number 1, which is choosing our function, which is f of x is equals to x squared plus 1, and our starting value, which is the x sub 0, is equals to 2. After determining our function and our starting value, we can now generate the sequence. In using our function, we have x sub 1, and our starting value, we have 2 squared plus 1 is equals to 5 modulo 91. And after determining the answer, we can now continue with the sequence by using the answer to the x sub 1. We can now continue to x sub 2, which is equals to 5 squared plus 1 is equals to 26 modulo 91. And to continue, we have x sub 3 is equals to 26 squared plus 1 is equals to 677, which is congruent to 40 modulo 91. After completing our sequence, we can now compute the GCD, and for the GCD, we have a formula of GCD and the absolute value of the difference of x sub 1 minus x sub 2 and modulo n. And for that, we have the GCD of 21, which is the difference of x sub 1 minus x sub 2, and the modulo n 91, and that will be equal to 7. And for our final step, which is the conclusion, we can now conclude that 7 is a non-trivial factor of 91. Let's now proceed with example number 2. In here, we have f of x is equals to x squared plus 1 modulo 187. Of course, we will be using the same function, f of x is equals to x squared plus 1, and our starting value is x sub 0 is equals to 2. If you're wondering why we're always starting with 2 and not with 1, it's because 1 is a factor of every integer. And now, we can now proceed to step number 2, which is generating the sequence. Same process as we did in the last example. We will use the function and the starting value, and that will be equal to x sub 1 is equals to 2 squared plus 1 is equals to 5 modulo 187. X sub 2 is equals to 5 squared plus 1 is equals to 26 modulo 187. And x sub 3 is equals to 26 squared plus 1 is equals to 677, and that will be congruent to 115 modulo 187. And for our last sequence will be x sub 4 is equals to 115 squared plus 1 equals to 13,226, which is congruent to 135 modulo 187. If you're wondering why we're creating a 4 sequence, it's because the GCD of x sub 1, if we use the GCD of x sub 1 and x sub 2 and modulo 187, that will result to 1. And we cannot have 1 as a result because that is given. 1 is a factor of every integer. So we will proceed with the sequence of x sub 3 and x sub 4. Now, after completing the sequence, we can now compute again the GCD. And our GCD will be equal to the absolute value of the difference of x sub 2 minus x sub 4. And that will be equal to 109. And our modulo n, of course, the 187. And the GCD of 109 and 187 will be equal to 11. And therefore, we can conclude that 11 is a non-trivial factor of 187. And next, we can also apply the refine checking. Step 1, we define the sequence. The sequence we did earlier, which is equals to x sub 0, of course, is equals to 2, x sub 1 is equals to 5, x sub 2 is equals to 26, x sub 3 is equals to 115, x sub 4 is equals to 135. And after defining the sequence, like we did earlier, we can now proceed to step number 2, which is equals to apply the refine check. In here, we have the formula of GCD of x sub 2k minus x sub k and the modulo n. Now, let's define what is k. Our k will be our starting value, which is equals to 2. And 2 is, as for our x sub k, we will be using x sub 2. And x sub 2 is equals to 26. And 2k, we will be multiplying the k, that will be equal to x sub 4. And x sub 4 is equals to 135. And after defining our x sub k and x sub 2k, we can now proceed in getting the GCD. And of course, the GCD of 135 minus 26 and 187 will be equal to 109 and 187. And of course, the same value as we did earlier is 11. This is just the short way of checking the factor of the modulo n. And that concludes our example, and I will pass the mic to our last reporter, will be Russel, for our summary.
Thank you, Michiko, for those clear examples. To conclude our presentation, let's wrap everything that was discussed. As what they said earlier, the power of this method lies in its efficiency. It is a Monte Carlo method, which means it uses a random-like process to find factors with up to 20 digits, much faster than trial division. The logic behind the name comes from the structure of the sequence. As a number repeat, they form a tail and a loop, creating that signature row shape you see on the slide. This behavior shows us to trap the factor within a cycle. In 1980, it made history by successfully factoring the Fermat number f sub 8, since f sub 8 was known to be composite back in 1909. Yet, it was until this method was used. Our objective is to find that non-trivial factor d. Once we detect a collision in the sequence, we use the Euclidean algorithm to calculate the GCD, which reveals the hidden factor. In short, Pollard's Rho is a clever, fast, and reliable tool. It turns a complex factoring problem into a simple search for a repeating pattern. That concludes our report. Thank you for listening, and we hope you learn and understand the Pollard's Rho factorization.